So this plot that we saw is an amazing confirmation about the fact that we have the essential physics of a blast wave shock propagation correct. Okay, the expectation of the theory, which is that R should be proportional to t raised to 2/2, which is represented by this line, is amazingly consistent with the data, and there are some interesting stories about the very first nuclear bomb explosion. About how the great physicist Enrico Fermi made a very quick order of magnitude calculation of what the velocity of the shock wave ought to be, right? Even when he was standing very far away from the blast site. Obviously, you wouldn't be standing close to the blast site. You would be standing several kilometers, several tens of kilometers away. And apparently what he did was he tore little pieces of paper, and as soon as he heard the sound of the blast, he just he let those pieces of paper just go, yeah, and he made a very quick rough calculation of the velocity with which these pieces of paper were moving. Okay, and from that he was able to say something about you see the velocity would be like something like this, right? So the velocity has the energy in it, right? So from the velocity of the piece of paper at a certain time, he was able to say something about the energy of the original bomb blast. And so you see, this is how it's an amazing demonstration of how simple ideas can be used to arrive at conclusions that are very important. Okay, of course his answer was just rough, but it was in the right ballpark, and for such a simple experiment it proved amazingly useful, and his rough guess was confirmed with more accurate measurements later on. Okay, so having now figured out the time evolution of the shock front, which is that R shock is proportional to 2/5 t raised to 2/5, we now ask what's behind the front. So you see, the shock has propagated. We need to know how does a shocked gas look like. Why is this? Why is this important? Because all astrophysical observations like this, all of this is essentially shock gas. All of this. This is in a sense that the shock has passed through the gas and it's heated it, and that's what's causing the particles to radiate, and that's what we see, right? So we would like to know what's the structure, what's the density structure, what's the velocity structure, what's the pressure structure behind the shock. Okay, this would be the shock front, so behind it, what's the structure, right? So that's what we would like to know, and let's see what does the shocked gas look like? Yeah, okay. Now we have the usual jump conditions for a strong shock. You remember this from our earlier discussion of shocks. The jump conditions for a strong shock. The subscript 1 would describe the undisturbed medium. 2 would be behind the shock, or the quote unquote shock medium that we just saw in the beautiful picture. Yeah. So so this would be the shocked density, and this would be the unshocked density. And we know that for an infinitely strong shock, in other words, a strong shock would be, you remember that the strong shock would be anything with a Mach number greater than approximately 4. Okay, for that, for such a strong shock, the ratio of the densities is this, and the ratio of the velocity, and this is not the ratio u2 over u1. It's slightly different. Okay, is 2 over gamma plus 1. These can be verified just from the shock jump conditions that we have derived earlier. Yeah, and I urge you to show this. It's a simple matter to show. Okay, and the pressure in the unshocked medium is related to the speed of the shock in this manner. Okay, all of these are fairly simple, straightforward derivations that follow in a transparent way. Okay, so that's that. Yeah. Also, I would like you to show this. Now, you remember we made all these deductions. We made these brilliant deductions. Not we, but the people who figured this out. They made these brilliant deductions using these non-dimensionalized variables. Right? So psi, this is what facilitated everything. So therefore, we now too, we don't want to be working with dimensional variables such as density, velocity, and so on and so forth, and pressure and everything. We would like dimensionless counterparts of the pressure, of the density, of the velocity, all of those. Okay, and so what are the best ways of doing that? We say so the primes would be the dimensionless density, and these are dimensional. So for instance, this. This and this are dimensional, whereas this is dimensionless. This is dimensionless density. Wherever you see a prime, and when it's, of course, when it's a function of the dimensionless distance psi, it is a dimensionless quantity, and simply from the symbol you should figure out it's a dimensionless version of what. In this case, it's a dimensionless. I put this in quotes because no density is really dimensionless. So it's like a density. Okay, it's a dimensionless counterpart of the density. Okay, so this is how I construct a dimensionless density. Similarly, yeah, and as it turns out, rho 2 is related to rho 1 in this manner, and therefore, this is how the dimensional density at a given radius and a given time is related to the dimensionless density. Okay, all right. Similarly, for the velocity, so this is how the dimensional velocity at a given radius and a given time is related to the dimensionless velocity. Okay, this is the dimensionless velocity, and the radius and the time appear here as would be expected. Everything else is dimensionless, you see, so the dimensions had better be r over t, and that turns out to be right. Okay, all right, and that's how the dimensional pressure is related to the dimensionless pressure. Okay, the reason we're doing all this is because we want to work with dimensionless variables such as rho, p, u, and so on and so forth from now on. And these are the this is the dimensionless density, dimensionless velocity, dimensionless pressure. So having related them to the dimensional quantities, we will see how they fit into the into the usual conservation equations. Yeah, so the dimension, I mean, here all we've done is related the P2 to the P1 more appropriately to rho 1 in this manner. Okay, right. So the dimensionless variables will be used in the usual conservation equations of mass, momentum, and energy. Right? Mass conservation, the usual in spherical in spherical geometry, of course. Because why? Because the geometry is spherical. The whole assumption is that the blast wave is expanding outwards, spherically. Yeah, and momentum conservation, we neglect viscosity. Okay, for inviscid flows is this. Okay, there's only one space variable, and that's r, and so there's a gradient of pressure. Gravity doesn't matter. Okay, gravity, body forces don't matter anymore. Of course, gravity is very, very important in astrophysics. Let's not get it wrong. But the point is, gravity has already done its job. Okay, it's caused gravitational collapse at the very center of the exploding star, and so the mass has contracted to such an extent that has increased the density to such an extent that it's ignited runaway carbon fusion, and because of this runaway reaction, there's a thermonuclear explosion, and from then on, it's like a point deposition of that thermonuclear explosion that happened is like a point deposition of an enormous amount of energy, and from then on, the fact that there's a massive core doesn't matter anymore. In other words, the gravitational attraction of the massive core doesn't matter anymore, and therefore we do not have a term expressing the gravitational force in the momentum conservation equation. Important to keep in mind. Okay, and energy conservation, I would urge you to, it's as if this is an advection equation. So this is kind of a advection equation. Advection equation for P over for this is what it is. Okay, you see d over dt plus u d over dr. So this quantity, this log p over rho raised to gamma, this is being advected along with velocity u, and that's the whole point, isn't it? The energy, and so this would be essentially especially if you think about a polytropic kind of gas where P equals K times rho raised to gamma log P over rho, this is just that K, and the K doesn't change. That's essentially what the whole adiabatic assumption is. The energy does not change. The energy is simply advected along with the shock with the speed u. That's what the energy conservation equation is telling you. Okay, right. Okay, now using the definition of the similarity parameter psi, you remember this, right? This is how psi is related to the dimensional radius r, right? We get, and this is very important, all of this you see here, there's a partial u partial t and there's a partial u partial r. So in other words, u rho rho p, all of these are functions of r and t, hence the partial derivatives. Okay, when you differentiate with respect to r, you hold t constant. When you're differentiating with respect to t, for instance here, you hold r constant. That's why you have these partial derivatives. So now, using this dimensionless variable, you see the dimensionless variable is let me write this again. U, for instance, u, or for that matter density and pressure, all of those are functions of both r and t. Okay, and so is psi. Psi is also a function of r and t in this particular combination. Therefore, what happens is a partial over partial t would be something like this. Okay, so this is a partial derivative whereas what is this? this is a straight derivative, not a partial one. Okay? And this is something that I want you to think about very carefully. Similarly, and this just follows from here, follows directly from here. Okay? Yeah, so you could stick a u here, you could stick a p here, you could stick anything here. So if you had d partial u partial t, you would have a du d psi. If you had a partial p partial t, you would have a dp d psi, so on and so forth. And this follows directly from here. Similarly, a d over dr, the partial over partial r is this. Again, this is a partial derivative, whereas this is a straight derivative. Now, what are we getting at? We're getting at, so we now have derivatives only in psi, not in r and t. Okay, not, I should say, not partial derivatives in r and t. We have straight derivatives, or this kind of straight d's in only in psi and not partial in r and t. But it gets better. In terms of, this is a lot of stuff, in terms of these non-dimensional variables, rho prime, u prime, and so on and so forth, and these straight u derivatives, okay, the conservation equations are, so this mass conservation equation, this guy, it translates, this guy essentially translates to this. Okay, so this is mass conservation in terms of rho prime and u prime, and the partial derivatives with respect to time and space have disappeared, and they are replaced by straight derivatives with respect to the non-dimensional variable psi. Okay, and this would be momentum conservation, and this would be energy conservation. Okay. Now, the main thing to note here, this is not just to give you a whole bunch of mathematics, but the main thing to note here is that earlier you had a set of coupled PDEs. These three were coupled partial differential equations, PDEs, whereas now the very same thing, okay, you have coupled ordinary differential equations. And there's a big simplification arising, of course, from the assumption that the expansion and everything is self-similar, admittedly. Okay, so you have coupled ordinary differential equations, and what's the big advantage? With ODEs, the number of boundary conditions goes down. As we all know, it's much easier to solve an ordinary differential equation than partial differential equations. By extension, it's much easier to solve a set of coupled ordinary differential equations, coupled ODEs, than it is to solve a set of coupled PDEs. Okay. In reality, one really should be solving the set of coupled PDEs, but if it's possible to make some reasonable assumptions about self-similarity or whatever, if it's possible to play a few mathematical games, then the price of those, making those assumptions hugely borne out by this huge simplification. The fact that you now arrive at a system of coupled ODEs rather than a system of coupled PDEs, which are much simpler to solve. So this is the final thing, right? And one can solve this and find solutions for the shocked gas, what the how the medium behind the shock looks like. And instead, so this is what I was just saying, instead of the coupled PDEs we started out with, we have ended up with coupled ODEs. And this is a consequence, of self similarity. And this is something I'd like you to keep in mind. As you go ahead, you will encounter other situations where you will be using self-similar variables, and this is one of the, you can think in mathematical terms, you can think of the motivation as just this. I try to choose a clever self-similar variable, for instance something like x minus vt. I call this something I don't know, some zeta, right? I start working in terms of this similarity variable so that I won't have to now work in terms of partial variables with respect to x and partial variables with respect to t. Maybe if I choose a clever combination of x and t, in this case this, and in case of this particular problem it was something else, it was another combination of r and t, but nonetheless it was cleverly chosen so that the set of coupled PDEs reduces to a set of coupled ODEs, and that's a big simplification. Okay. Now the boundary conditions for solving these coupled ODEs are, let's just say that at some reference psi naught, okay, the non-dimensional density, velocity and pressure are all set equal to 1. Anyway, we are non-dimensionalizing, these are all non-dimensional quantities. In order to get the dimensional quantities, we would have to multiply with appropriate normalizations. Okay, so the actual values will be taken care of by those normalizations. For simplicity, we take the non-dimensional condition, the non-dimensional boundary conditions to be just all equal to 1. Okay, that makes things simple, right? Where of course psi naught is a shock location. At the shock location, all of these are equal to 1, and this is how the solution to this set of coupled ODEs looks like. Okay, so the x-axis is the dimensional variable over psi naught, okay, and the y-axis is essentially rho prime, u prime and p prime, all of these. So this represents p prime, this represents rho prime, and this is u prime, and the shock location is here. Okay, so this is psi over psi naught, and psi over psi naught is equal to 1, which means that this is where the shock location is. So behind the shock, this is how the pressure varies. The pressure decreases in this manner. Yeah, the density decreases like so, and beyond a point it flattens out. The velocity keeps decreasing. Okay, so this is how the shocked medium looks. The shock is propagating into the interstellar medium like so. It's going ahead. What does the shocked gas look like? What is the density, velocity, pressure and other things in the gas that has been subject to the shock? What does it look like? It looks like this. The density looks like this, the pressure looks like this, and the velocity looks like this. Okay, given these, you can put this into maybe a radiative transfer code or something, and try to figure out, say from the pressure and the density, you can try to figure out the temperature of the shock medium, and from the temperature you can say something about, assuming of course, if you make the assumption that the radiating gas is a black body, you can say something about what regions of the spectrum it will be radiating in, and so on and so forth. So you can make lots of interesting deductions about the shocked medium, about the medium that's been subjected to the shock. In other words, all of this stuff. Okay, so the graph that I just showed you tells you the structure of the density, of the pressure and velocity and everything inside from here backwards. And having known that, one can put that into other radiation processes considerations in order to see what to expect of the emitted radiation, and this is the actual observation, and you confront the observation with the expectations from the theory, and try to see if we have an accurate depiction of what's going on. So you see, this was an illustration of how fluid dynamics, fairly simple fluid dynamics ideas, are used to attack a grand problem such as supernovae explosions. So we will stop here for the time being. Thank you.